Alright, welcome back to the final review. Let's go and wrap it up. So we were talking about recursion last time, and so we did the simple factorial example, the one we all know and love. And now let's do a slightly more complicated example with trees. So let's do an example that's a recursive tree algorithm where we're going to count the number of leaves recursively. So let me draw a nice little tree here. So here's the root of our tree. And let's break this down. This leaf counting idea is a recursive idea. Let's figure out why. So this does not have to be a binary search tree, but I guess I'm going to draw a binary search tree. That's the example that I made in my mind. Okay, let's do that. That's a 7. And then one more. Let's do, I guess 9 can go there. Okay, so I claim that this is a recursive problem. So we need to go and, looking at this tree, can we break it down and count the leaves recursively? Alright, so when you're doing tree recursion, usually you're going to break it down into the left and right subtrees, because here you have smaller trees that you could solve the problem on. So you just get to assume when you make your recursive calls, like you go down the left side, it will correctly give you back. You get to assume that when you make the left side's recursive call, you're going to get back the correct number of leaves in this subtree, because it's a smaller tree. That's the magic of recursion. And so there's one leaf in this subtree, so assume that we got back a 1 there. Alright? And then, here's this one. You make this call down the right side recursively. What are you going to get back? What can we assume to get back? The correct number of leaves, right, for that smaller subtree, which is 2. So we get to assume that we get back 2 there. And what's our final answer for this full tree, because that's the last piece of the puzzle for the recursive case? Well, it's going to be the sum, right? 1 plus 2. This doesn't really count as a leaf or anything. It's just like how many leaves were in the left side plus how many leaves were in the right side. And that will turn into your recursive case. Alright? So that's going to be the secret there. There's your recursive case. It's going to be like, alright, I just want to count the leaves. Count leaves of the left subtree, root left, and add that answer to the leaf counting, right? Recursively count the leaves of root right, the right subtree. Those are smaller calls. Assume they do the right thing. We're going to build up the correct answer with their addition. All right, so that's the secret there, and that will be the recursive case. And then the final piece of the puzzle is what do we do? There it goes. What do we do for the base case? Like, what should the base case be? And so you have to think about small trees, because usually it's like the size 1 tree or empty tree that ends up being your base case for tree stuff, for tree recursion. So let's think about this tiny little tree here. What do we want? Like, we're coming in from the root here, and we're going to make a recursive call left and a recursive call right. What should happen, right? So there's nothing to the right, first of all. How many leaves are over here to this to the right side in the empty tree? How many leaves are there in the empty tree? There are 0, right? That sounds like a base case. And then also, this right here is a leaf, right? This one node. We're also going to have to code that up too, because if you think about it, like, the recursive case will not be correct for 0 plus 0 if you went down to the leaves there. Or if you went down to, the empty trees there. So I think we're also going to need to stop at a size 1 tree. If you have just one tree, if you have just one node left, and that is your entire tree, then it is a leaf. All right, go look left, look right. Notice that you're at a leaf. How many leaves are there in this size 1 tree? There is 1 leaf. Okay, and so it seems like we're going to need 2 base cases. All right, that's going to hopefully work out. And I hope you see how we found that. Just like, all right, look at smaller trees, what needs to happen here? So an empty tree, if you ever see the empty tree, it has 0 leaves. I have to cover that for sure. But also, that's not good enough. That plus these is just going to put 0 everywhere, right? It's going to be 0 all day long. We actually need to notice leaves as well. So if you ever see a leaf, a single leaf all by itself, that's your entire tree, then the size of that is, or the number of leaves in that tree is 1. All right, and so that's going to eventually give us real numbers for the recursion to actually compute. Okay, so that's the secret there, and I have coded this up already. So here it is, and here's the tree as well. So here's my tree, 5, 3, 8, 1, 7, 9. I've hooked it all up right, so that the data is the left and right pointers. So it's all there. The root of the tree is the 5 node. Like, I've got this tree set up, and I've got my count leaves function that takes the entire tree by getting a pointer to its root. So here it goes. These are what tree nodes look like. And so here are my 2 base cases, and then my recursive case. So, all right, if I got the empty tree, there are no leaves in the empty tree, so return 0, nothing in there. Otherwise, if I myself am a leaf, then notice that, right? I've got nothing to the left and to the right of me. Then there is 1 leaf in this tiny little tree that's just me. And then otherwise, if I'm at like a for sure internal node, and I've got more work to do in that case, right? So I'm going to count the leaves of my left subtree and my right subtree and add their answers back up. And that will correctly count the leaves in the whole thing. And so I do get correctly the number of leaves in this tree is 3. All right. So it makes its way down, eventually hits the leaf case 3 times, and it propagates that answer. So that's pretty cool. All right, so that's recursion. You're not allowed to forget. Let's next talk about the big 3. All right, we love them now, right? We got the copy constructor. You want to copy somebody else into you. You've got the copy assignment operator. You've got something in yourself right now, but you want to forget about yourself and copy somebody else into you now. You've already been constructed. Remember to return a reference to yourself. And then a destructor is when you're ready to get rid of yourself. Like, what else needs to happen? Is there any extra cleanup work? And we notice that we need to overload all 3 of the big 3 whenever we're doing heap stuff. So the second we start allocating our own memory, the defaults of all of these are bad. All right. So with I've got an example for us. Let's make a class called holder R, because I already made one called holder in the original lectures, right? Let's make a holder R class that holds on to an array of a certain size n that we give in the constructor. So like, here's what the normal constructor is going to look like. It'll be holder of an array, call it h, and it'll make like a heap array of size 42. So that's the job of it. It's going to hold on to an array on the heap of a certain size. It will build that in the normal parameterized constructor. So that's the setup right there. That's what's going to happen in the normal constructor. And then let's think about the rest of these. All right. So the job of the copy constructor is to bring somebody else into you, right? So like if somebody says holder, let's just draw pictures for all of them. Holder R, I don't know, H2 based on H. Then we would like to do a deep copy, right? We like to do a deep copy, make our own new array on the heap of the same size, and copy it all into there, right? Does that make sense? That's what we'd like to do. That's the goal there. Bring it all the way in, all right? So we're copying it all the way in with a call like that. Let's see what else. If we have some other thing later on, and we'd like to replace, that's the job for the copy assignment operator. We've got somebody else like, I don't know, h2 equals, I don't know, h3. If that ever happens, then we'd like to drop our current stuff, right? Drop our current stuff, get rid of whatever was there, and like add in the new stuff, right? Make a brand new array on the heap, chop off this pointer, delete it from the heap so that we don't leak memory, and like make a brand new array of whatever this one's size was and copy it all in, okay? So that's the goal there. And then finally, when things are meant to go away, the job of a destructor is to go into like the heap, for example, and delete any extra memory. Okay, so let's think about all those together. And just remember that in the copy assignment as well, we're going to return a reference to ourselves, and we also have that self-assignment check. So let's actually go to code now. All right, that was enough words. So let's see. I've got a class called holder R. And what it's going to do is it's going to hold on to an array on the heap. So it's got int star R as a member variable for sure. We're going to need that. And then we'll also need to know its size. So, okay. What do we want for holder R? We'd like to be able to construct one normally, just like an int. So here's kind of what I want to do, right? Holder holder R H of size 42, and then I'd like to be able to like copy that into somebody else. So like holder H2, make it in H's image. That's the call to the copy constructor. And then I'd like to be able to like make a new holder as well, like H3 or something, like it's already been made, and then copy somebody else into me. So like H3 equals H2. Okay, so that's a call to the copy assignment operator. All right, so those are the kinds of things I'd like to have. And then the destructor is going to be called right as we're returning from main. So everybody's going to go away because they were on the stack. So let's do all those things. So I need holder R, the one that takes an int. I'm just going to be lazy and implement all this inside the class. So there's that one. Then I'm going to need copy assignment. Or sorry, let's do copy constructor first. Holder R with somebody else, const holder R reference other. Then do something. Might as well just copy these other ones in there. It's almost the same words, right? It's holder R though. Copy assignment, and then the destructor. What needs to happen for all these guys? Okay. So for the normal constructor, let's see if I can split screen this and show you like how we're using these things. For the normal constructor, it's just make an array of that size on the heap. So we've got a member variable called R, right? There it is, called R. And we also have a size as well. So our array, we need to make it on the heap of size n, and that's the size of that thing. We need to save it just in case we need to pass it along to somebody else. All right, that's how they know how big it was. All right, so for a copy constructor, we'd like to deep copy others array into our own. Okay, that's what we want to do. So also set our size to other.size, and then set our R now equals to new int of whatever that size was, and then we want to copy whatever was in other, all these things, into this one, all right, into that new one. That's the goal. So it's going to need a loop. So int I equals 0, I is less than size I plus plus. My R of I is equal to the other's R of I. All right, so it's a deep copy. Brand new array with the same elements though. So that's the copy constructor. The copy assignment operator, its job is going to be like, I've been made, I've been constructed already. Like H3, for example, I've been constructed already in some other way. I've got my own array on the heap, but I'm done with it now. I want to replace what I had with this other thing. All right, so I'm going to deep copy this other thing into me after getting rid of my own stuff. All right, so I want to delete my own stuff, essentially. All right, so like delete our own array. And I'm doing this wrong right now. I've forgotten the self-assignment check. I'll get to that in a second. All right, delete bracket bracket R, that's the one thing on the heap, right? And now I want to deep copy others' stuff into ourselves. All right, so there's that. And that's pretty much the copy constructor, right? All this other stuff. I can mostly copy it. Just like that. Okay? The last piece of the puzzle, though, is I need to return a reference to myself always inside of the copy assignment. So you can chain equalities, chain assignments. So that's a return star this. Right? So that's mostly correct. But I've forgotten the self-assignment check. So there's one less thing that we need to worry about, right? What if I do this? What if I say, I don't know, H2 equals H2 or something? That's another call to the copy assignment operator, but I'm putting myself into myself, which doesn't really make sense. But what should this do? Essentially nothing, right? Because you already are yourself. But what will the code do right now? Well, it's going to delete myself and try to copy my old pointer into myself again, which is, it's not going to work. Now I'm going to be accessing, right, other.r is my own array that I deleted. I'm leaking memory. Or sorry, I'm not leaking memory. I'm using reclaimed memory essentially at this point. And so that is totally undefined behavior. That is a no-no. We do not want to do that. And so we got to watch out for self-assignment. If anybody tries to assign themselves into themselves, we better just stop early. There's nothing to do. You already are yourself. Okay, so if the only way to check for that is to look at the addresses. If the address of other is the address of me, that means we're the same. Then I'm done. Just return star this, call it a day. There's nothing left to do in that case. So that's the copy assignment. So it's like delete yourself and then copy somebody else into you. And so essentially, right? Essentially, once we get to the destructor, this will make extra more sense. So essentially, this is the destructor, which deletes stuff, plus copy assignment. Or sorry, copy constructor. And then also don't forget about the self-assignment check. That's just extra. But it really is kind of a combination of those two things, right? Because all this code right here was the copy constructor code, and this is going to end up being the destructor code. So when we want to go away, what do? When we're being destructed, well, all the local stuff is going to go away just fine. It's just the stuff on the heap that we need to take care of. So it's just the array. We need to delete the array off the heap, and that's going to be delete bracket bracket r, because it's an array of things, and that should do it. So you see how now the copy assignment is really just destructor plus copy constructor plus returning the right things and watching out for self-assignment. So yeah, that's all that code all together, all working nicely. And yeah, I haven't output anything, so we're not actually going to see anything, but let's just make sure we don't get any seg faults. We can also do val grind. All heap blocks were freed. No leaks are possible, so we're also not leaking any memory, which is perfect. Okay, so yeah, I think that's what I wanted to show you. I hope that makes sense and it's reminding you of things. So feel free to study that and ask me questions about it. That's the big three. What else do I want to talk about now? Let's go to just complexities in general. You're not allowed to forget the complexities of all the data structures that we talked about. This nice little website is mostly correct. You do have to take it with a grain of salt for a lot of the things that we've learned. So like the worst case complexity for like linked lists is a little bit off. For hash tables, yes, in the worst case it's O of n, but I'm sorry, where's hash table? But in the average case, it's constant. Like we've talked about those things. For a binary search tree, worst case, for all of these things like insertion, it says O of n, even though really like we think of it as O of h. All right, so like you've got your quicksort algorithms and all those fun sorting things as well down there. So like this is mostly correct. You just gotta think as you use it. Linked lists, especially what we did in this class is we did singly linked lists, by the way. And so list insertion and deletion, it says is constant in the worst case, but that honestly matter. It depends on where you're putting the thing. All right, remember that you need pointers to what the thing that you're getting rid of. So like if this is your list and it starts at the front here, a singly linked list. It's very hard to like delete this node correctly, all right? Even though this website says deletion is constant, it depends on whether you have a pointer to the previous thing already. So remember that in singly linked list land, to get rid of this node and to make this the correct final thing, is you have to iterate to it. You got to get all the way down to this guy, starting from the front. There's no way to go backwards in a singly linked list. So you got to find this node, which is a linear time thing, and then like, okay, now I can set the next and like do the deletion. So it is not perfectly correct. It's like, I think it's thinking of deletion as like, all right, I'm popping the front always or something. But just take this with a grain of salt. It is helpful though, right? All these ordered trees, like look at their logarithmic time worst cases. That's all beautiful. So what else? And yeah, just remember that the the normal tree stuff, like our binary search tree, insertion, deletion, search, and all that, we thought of it as O of H. O of H. It says O of N because technically your BST could look horrible like this, and like the height of the tree is the number of nodes, but that's not as helpful during the analysis, in my opinion. So that's why we did it O of H instead. But O of N is technically also correct. All right. So yeah, that's a bunch of old stuff you can't forget. Let's now fast forward and talk about some newer stuff that came after the second midterm. So we've got heaps, very important. The data structure, not the place in memory, right? We've got the heap in memory. That's your dynamically allocated stuff. That is completely different from the data structure heap, right? Remember that. So this is used in the priority queue ADT, so you can like always get the maximal or minimal thing. But what a heap is a complete binary tree, right? Filled in as much as it can, all the way until the last level, and that last level is stored from left to right in order, right? And we are somehow storing that complete binary tree inside of a vector, which is crazy but cool. And the whole job of a heap is to give you access to the minimum or the maximum value very quickly. It will always be the top of your tree or like the 0th index in your heap array. Okay, so let me draw, for example, a min heap. Max heaps are the opposite. Sorry, I said one thing and wrote the other. So min heap. Here's an example of a min heap. Let's say we've got 4 is the smallest thing. It'll be at the top. We think of it as a tree like this. This can be, I don't know, 42, 5. It's not a BST because you can do it like this and it's still correct. This can be what, 47. This can be 88. Let's say this can be well, we've got to fill it in from left to right. It's got to be complete. So I got to fill in these guys. This can be 100. This can be 256. This can be 112. So it's completely out of order as far as BSTs are concerned. But it's a different kind of tree, right? All the nodes respect the heap property. These all respect the min heap property where, look at all these guys. They're all less than each other on the way downwards. Do you see that? That is fine. That creates a heap, and that's going to force the smallest thing to the top if you follow that rule at every node. That's the beauty of heaps, okay? And so we think of it this way as a tree, but really we're storing it as an array or a vector. So here's what the heap array looks like. It's really just a big long array or a vector in order. And here's the order. This is index 0. This is index 1, 2, 3, 4, 5, 6. It goes in that level order, 7. So the very first thing in the heap array is the node 4. The next thing is the node 42. Then the node 5. All right? Then the node 47. And so on and so forth until you get to the last thing. That's what it looks like. Okay, so it's very quick to find what you're looking for, like the minimum. For example, in a min heap, you can always just go to index 0. That's the thing. It's there. Go and find it. All right. Because this tree is complete, it is balanced. And because it's balanced, we get logarithmic time for a lot of cool stuff. So here is, do we have heap in this? Not really, do we? But it's logarithmic anyway. All right. So lots of logs because it's balanced. So we've got, let's see, pushing, for example. Pushing to a heap is like you add something here, right? You add, I don't know, maybe 7. And then you got to move it up the tree, potentially the height of the tree, which is logarithmic in terms of the number of nodes because it's balanced. Isn't that beautiful? So that's push, it's log of n. You insert at the end, and then you bubble up. So like you push back, that's index 8, and then you move it up as far as it needs to go. And it's quick to move around the tree as well. Like you think of it as a tree and you use indices to move around. Like it's always the case that if you want to go to the left and you're at some index, the left child of u is always index 2i to your index plus 1. And that works everywhere. 2 times 0 plus 1 is 1. That's the left child of that one. 2 times 2 plus 1 is correctly 5. You're always going to get the correct left index. 2 times 3 plus 1 is 7. It's always going to work. So there's formulas like this for left, right, and parent. And they let you move around the tree as it's stored in an array, which is cool. Pop is logarithmic time. You always only pop the root. What you do is you swap it with, like you're going to swap something with the root, the bottommost, rightmost thing. and then you're going to bubble it down, like you're going to move the 112 up here. You can pop back, and then it needs to like be moved down, and like the 5 needs to come up, and something like that. But you're going to move it down to potentially the height of the tree, the new height of the tree, which is going to be logarithmic in terms of n. Okay, so let's swap with the root, and then you bubble down. And yeah, peeking, looking at the top of your heap is very easy. It's just like go to the index, that's constant. Checking to see if it's empty is constant, because that's just like use the vector operation. Same with length. How many things are in my heap? Just like the size of my vector, if I'm using a vector. Yeah, so that's heaps in a nutshell, in drawing form. What else do I want to do right now? Yeah, let's talk about some of these algorithms. Let's do like a push. All right, here's my example min heap. Let me copy and paste that a few places. Whee! So I've got it, and let's see. I guess I want it here as well as here. We'll talk about push and pop in detail. All right, so let's go and let's do push. So let's say I want to push something into this heap. Let's say I'm going to push a brand new thing, and that happens to be the minimum thing. So let's push the number 3. All right, so initially what we're going to do when you push a node, or you push a value into your heap, it adds a node to the next location in the heap array, which is the end, the last index, which is going to end up being the bottommost rightmost thing. So it's going here, index 8, whatever you're pushing. And let's say we're going to push 3. All right, and then this node does not reflect or does not respect the heap property, because like 47 and 3, like the 3 should be higher up in the tree because it's a min heap. So what you got to do is you got to bubble it up or percolate it up. Okay. And what that means is you just keep swapping with your parent as long as your key is smaller, like you belong higher up. So it's 3 versus 47, they got to swap. So the 3 comes here, 47 goes here. And now it's 3 versus 42. We're still not yet reflecting the heap property at all the nodes. So this 3 needs to move its way up some more. So we'll do a swap here. So this can become 42. This is now 3. And then still, right, 3 versus 4, now look at the parent, it's still out of order, so we'll swap. This becomes 4, this becomes 3, and that's the new root, all right? And so you're going up potentially the height of the tree. If you're adding the new minimum thing, then that means it's logarithmic time in terms of the number of nodes, because you might go all the way to the top like that, all right? That's the height of the tree, and the tree is balanced. Beautiful. So that's push. Pop is kind of the opposite. So if you want to pop, you're only ever going to be able to pop the root, like you want to get rid of the root. What you do is you turn it into a simpler problem. Instead of popping the root and getting rid of this node and like reshuffling everything, what we're going to do is really get rid of this node. All right, so we're going to put the thing we don't like down there. All right, so to pop the root, you're going to swap it with the bottommost rightmost thing. So this becomes 112, this becomes 4. Technically you don't really have to put 4 here because you're going to get rid of it, but let's think of it that way. And then you can pop back the vector, which is a constant time thing. It's like, all right, get rid of this because we don't care about it anymore. Now index 7 is gone. And what we've done is installed somebody new at the top here. And we got to bubble it down to where it belongs. So it's 112, does not belong at the top because it's got smaller things below it. So what you do is you always are going to look at your children, you're going to percolate it down or bubble it down, and you're going to put it, you're going to swap with a smaller thing because that's the thing that belongs up top. All right, so 42 versus 5, 5 is smaller, and so you're going to swap this guy with the 5. So 5, that's how you keep the heap property reflected. It all works out, everybody's happy. And so now that the 112 is here, you still got to bubble it down further because you've got something smaller than it, all right? Doesn't matter that one node's not smaller than it, you still got one node that is smaller. And so it's like, all right, if there's somebody smaller, I'm going to swap with the smaller of these two nodes, because 112 needs to go down. So 112 and 100, we're going to swap. So this becomes 100, this becomes the 112 now. Okay, so that's it. And now it's in the right spot. You just keep on looking at both children and swapping with the smaller one if there is a one that is smaller than you. All right. So yeah, that's pretty much the name of the game with pop. And again, because of that process, you might go down the height of the tree, and that is going to end up being logarithmic time. Okay, so yeah, those are your heap operations and some drawings to go with them. What next? We got sorting. All right, can't forget about sorting. Honestly, all I really care about you remembering, because like you can always go and look up the algorithms, is just like kind of remember how they work and what's happening. All right, so just remember the basic ideas and the running times of all the sorting algorithms. bubble sort, for example, was your worst n-squared one, because it's very zoomed in, and it keeps swapping elements that are right next to each other. All right, so if they're out of order, so bubble sort, you click it, just always looking at the two things right next to each other and swapping them. Like, all right, are they out of order? And if they are, it's just gonna like do the swap, and that all that really does is move the biggest thing after one round of going through the array. It moves the biggest thing to the right side, and so then you never have to touch it. And so you have a smaller and smaller array to work with each time, but you still need to go and look at each pair of things that are right next to each other, swap them if they're out of order. So like these small things, like this small node right here, this number 3, it's being swapped each time. It needs to make its way all the way mostly to the left. And like it's going to take a few rounds. It's going to take quite a few, right? n-1-ish rounds to get there if it was all the way to the right. So it's very, very slow, and it's n squared. It's a big, long nested loop. So you got to go through the entire subarray size of the array times. So it's n times n. All right, so that's your average case and the worst case for bubble sort. It does have a nice best case if you program it correctly. You'll notice that like it'll keep swapping elements next to each other, and like it'll figure out it doesn't have to do anything else. But that's only if you have a good implementation. This implementation is naive, and it's just not going to do it right. So you could have a better case if your array was already sorted and you watched out for that. Okay, so there's that. Let's see here. Selection sort. We got selection sort next. That is, let's see. That's going to be, let me randomize the array first. What selection sort does is it's going to go and select the minimum each time. It keeps finding the min value of the rest of my array and putting it in the right spot. So it's going to highlight, there's the 1, it's going to bring it to the end. It's going to, like, here's its current guess, and you see it, its current guess of the minimum, and you see it like updating its guess each time. And then it's going to like put it in its right spot, because the new minimum goes in the next open place. And so it's slowly but surely sorting the array that way. And so it's going through a smaller and smaller subarray each time, finding the minimum and doing a swap. And so that ends up being n squared in the worst case and the average case, and even the best case. It's like it's always going to try to find that minimum. So it's got a smaller and smaller array to work with each time. Just go find the smallest thing and the rest of the things left, and the rest of those elements left, and put it in the next open spot. So yeah, there's selection sort. Insertion sort is probably the best of the n-squared algorithms. It works a little bit different. It's going to keep a locally sorted subarray. After each iteration, it's the first original elements. So like if I sort it, after like three iterations, it's going to be like the original elements of the array are in sorted order. It's not going to bring in something very small like this 6 that really needs to go at the start. It's not going to bring it over until like we open up our frontier to get there, and then we're going to move it all the way down to where it belongs. So that's the difference between it and selection sort. It's going to sort the original first elements. It's going to keep track of a locally sorted subarray. So it's like, you see like it's increasing now. It's sorting those original elements in that original order, and then it brings in a new thing down to where it belongs, brings in the next thing down to where it belongs, brings in the next thing. And so yeah, it's a useful algorithm. There's the 6 finally going where it needs to go. So sometimes it moves things, if they're small, it moves them farther than bigger things, because the bigger things they're kind of close, right? They don't need to move down as far. They belong closer to where we started. So yeah, this is the best of the n-squared arrays, because it's like, it's not as zoomed in as bubble sort, and it also has a really good best case, has a linear best case, because if the array is already sorted or close to being sorted, then you click it, it's just got to look to the left, like bring in the new thing, like is it in the right spot? Yeah, everything is smaller, and so it's good to go. So that's really nice. All right, so linear best case if the array is almost sorted. So even if there are a few things out of order, it doesn't have to move them far. It moves them a constant number of places. That's insertion sort, and those are all n-squared. The two good ones, right, the n log n ones, are merge sort and quick sort, and they require recursion. All right, so merge sort is n log n, best case, worst case, average case. What merge sort does is it's going to divide and conquer. It's going to take your array, it's going to chop it in half, find the midpoint, and then it's going to recursively call a merge sort on those smaller arrays. Two smaller arrays, you get to like, all right, those are smaller things, I can merge sort them, and so then you end up with two sorted smaller arrays, subarrays, and then you merge them back. You need some extra memory for that, but you merge them all back, and it's just like it's a game of, that's a linear time process. It's a game of like, all right, look at the first thing, because these are the two smallest things, which one wins out for this new spot, the original spot, the next spot in the original array. And you just keep on playing that game for all the new stuff. And so it's a bunch of recursively call merge sort, and then once the things get sorted, merge them back. Okay? So it's always split exactly in half, recursively sort both halves, and merge them back together. It does take linear space. The space complexity is not constant for merge sort. It needs a little helper array down here to do the merging. But you see it, like it's got some sorted subarrays, and then it's merged them back. So now it's working on the right half of the array. The right two quarters being merged, then it's merging back those two sorted subarrays. And so very much faster than the other ones, right? I wasn't even done talking and it was finished. So there's that, and then there's quicksort. Quicksort is kind of like the best. It's got n log n as the average and best case. It does have a worst case that's n squared, but usually you never run into it if you do a just like a normal amount of like randomization. Randomized quicksort is always n log n, unless you have a really, really bad day. It's very, very unlikely. So what quicksort does is it calls partition first, a helper function called partition, that partitions the array based on a pivot. It puts everything less than that pivot value on the left side of the array, and everything bigger than the pivot on the right side of the array. And then it's got two smaller arrays after that. That's got smaller things and bigger things, and it keeps on recursively quicksorting those. And then also partition, once it's done, it figures out like, all right, everything to the left is smaller than the pivot, everything to the right is bigger than the pivot. And it ends up like knowing where the where that pivot element belongs after that as well. So let's watch a picture of that. It'll draw an arrow to mean, or a line to mean that's the pivot. Everything to the left of the pivot is going to be placed on the left side of the array. Everything to the right of the pivot, everything bigger, is going to be placed on the right side of the pivot. And then once it's done doing the partitioning, it knows where the pivot belongs. That's what I'm trying to say there. And so, yeah, that's quicksort in a nutshell. It does have a bad worst case, just if you do something silly like this. If you end up picking really bad pivots that like partition based on like, what is it? Like if you partition based on like this element, like the second element or something, and so like you've chopped off the array like this. You got a one size subarray to quicksort over here, and a giant size subarray to quicksort over here. And if you keep on doing that somehow, like you're picking really bad pivot element values, then you're splitting up your array like this, and it takes essentially the size of the array to reach the end of the recursion. And so that's the problem. But usually you'll just pick a random pivot, and that will like and make its way usually towards the middle, and that will do the correct logarithmic time splitting of the array. So yeah, that's sorting in a nutshell. Yeah, just go back to your book and go back to the slides for the actual details, but those are the words I want to say, I think. Then we also talked about just like commands on the command line, Linux and Unix commands, so you're not allowed to forget. So first of all, like when you're moving around and going places, you're working with paths. We call them paths, right? Paths in your file system. And so there is a root of the file system. Like if I look where I am right now, I am in pwd. That's my current folder is all this weird stuff. But yeah, let me open up a new terminal. So I'm still in that same folder. If I want, I can go straight to the root directory. That's like the outermost directory. It's just called a slash. You can't go out any farther than the slash directory. That's your root directory. And then there are folders inside of that, right? You've got all these things, all these folders. You got dev for your devices. You've got home for all the users' home folders. You've got etc, which people tend to pronounce etsy, that holds some cool files and configurations. And you got plenty more where that came from. So home is a folder with other people's home folders in them. So like your tilde is stored in the home folder. So like I've got one for my account. Maybe I can make one for my cat's account, and then you can have more and more folders and files within them. right? So that's like the structure of the file system, and you can move around, right? With slashes. Like if I know exactly where I want to go right now, I want to go to /home/my username /my Windows desktop /F24 code from class, type tab to save yourself some typing, /CSCI41 /lecture31. Like that's a big long path name, and you split it with slashes. And you also start it with a slash because that's your root directory. You can also use it relatively through like your home folder. So cd tilde is always your home folder. That's always you right there, whatever you're logged in as. And so you can make it a little bit faster on yourself. cd / Windows desktop, blah, blah, blah. There. Now I'm back to where I wanted to be. So that's kind of the idea. You can move things around. You can move around with cd. Cd ... gets you back out into like in the outer folder. So now I'm in just the CSCI41 folder and not a lecture folder. So now I'm in the lecture folder. So ... is a useful one. Yeah, what else do we have? I just want to show a few ones, I guess. Let's see here. Let's do like some of these. So let's make a let's make a new folder, I guess, with makedir. I'll say makedir new folder. That'll be its name. And so now it exists, and I can cd inside of it. And then I can let's make like a file. Let's make like a test file. And one way to make it is to like echo into it. Echo, just like print stuff. So hello world. Prints that out to the screen. I can redirect that output into a file. I'll call it test.txt. So now I've got that file. I can print it back out with cat to concatenate it. I can copy it with, let's see. I can copy it with a cp command. So let's do that. I'll copy test.txt into a file called testcopy.txt. And so now I've got two files, and they both hold the same thing. So testcopy also has hello world in it. I can move files back out to other places. Like I can move this test.txt into the parent directory. So now it's not here anymore, but it's outside. It's in this directory now. So there's test.txt. Now it's in just the lecture31 folder, and I can move it back inside of that new folder by just saying its name. I can also rename it with the new folder and then like test2.txt. Like I can call it something else as I move it as well, or I can just give the folder I want to put it in. So now it's called test2. Move it into just test. So move also can move between folders and rename files. You can also do both at once. There's also rm for deletion, for removing things. So like, let's make another copy test into test2.txt. If I don't want that file anymore, I can remove it with rm. Boop, so now it's gone. So yeah, I think that's pretty much what I wanted to say for all those. If you are using Nano still, shame on you. All right, that is a crutch. It is not going to get you much farther in your computer science career. Vim and Emacs are much, much better. I guess I've tried to convince you to use Vim because that's what I'm using in class, but like these are all competitors with one another. There's also Visual Studio Code if you want to learn like a graphical program, but like get yourself out of Nano by the end of this class, or your life will not be very fun in future classes, I promise. Okay, so just keep that in mind. You have been warned. I guess the last thing I want to say on this slide is the make command, like the make files and the make command. I've been giving you a lot of make files. I just want to remind you what's happening with make files. They're very, very useful. They allow you to like give a recipe for exactly how to build your final project, and also to do it in the most efficient way with separate compilation. So let's talk about that first. So what separate compilation means is you're going to compile each of your CPP files to .o files first. So like you've got an a.cpp and like a b.cpp. Don't just give those to G++. What you should do is give them, like, let's say these work together and they're like libraries and one has the main function. You should compile them separately into .o files. That's machine code for that one file. So a.o, that's a compilation process. So create the machine code for that one file for A, and then also for B, make b.o. and that's going to allow you to, that's the compiled form of just b.o. And then once you got both of those, then you link them together, all right? So then you link them together into some final executable with the linker. Maybe that's the linking process into maybe a file called like main or something. And the whole reason to do this two-step process is if you only change b.cpp, you only have to recompile b.o, and then you relink it. Linking is fast. Link it with the old a.o. So you're saving a lot of work. If you had like millions and millions of files, it would take hours to compile stuff, even if you just change one file otherwise, okay? So that's the goal of separate compilation. You only have to recompile what changed, and then you just link them all together at the end, which is a very fast process. All right, so let's do an example with like a library and like a main function. So I'll do an a.cpp and a b.cpp. So let's do that. So here I am back in my lecture 31 folder. Let's get back out here down here as well. Let's make an a.cpp. It's gonna hold my main function, all right? And then let's make a header file for a library, like a B library, all right? And I'll include that here. I'll get to that after I make it, I guess. So let's make a new file called b.h. Remember your header file guards. And let's declare in this library, we're gonna make a foo function. Just like that. All right, so that's the function I promised to make, and let's go and actually implement it in b.cpp. So I'll make a new file called b.cpp that will customarily you include your library, and then we'll implement our foo program. So what should we do for foo? Let's just be like return x + 1, just a simple implementation. And now we can include it over here in the a.cpp file. We can include our library by including its header, and then we can call it. It'll be like cout foo on 42. All right, so that'll work. And normally, if you were lazy, you would compile it all at once. Be like g++, give a.cpp and b.cpp, call the thing main. And that works, but you don't get the nice savings, the time savings that comes with separate compilation. So let's go back to nothing, and let's make a makefile. All right, what we'd like to do is do a two-step process. Do like a g++-c on all the .cpp files. That will make a.o. And then same for b.cpp. That will make b.o. There that is. And now we want to link these two together with one last call to g++. And then call it main. Like those are the things we'd like to do now, and like /main will run it. So let's remove all those files. Remove the .o files and main. Get back to just blank slate. And now let's do it all in a makefile. We want to automate the process with a makefile. So I'll make a new file called just makefile. And it will make it very easy for me to keep track of that separate compilation process. I just write it once, and make will take care of the rest for me. So here's a makefile. Remember what they look like. Every makefile rule, it's made up of a bunch of rules, and every rule looks like this. It has a target name. That's what you're trying to get at and trying to create. It's usually the name of the file. And then you give some requirements, or your ingredients. They come after a colon. And then you tab over and give the body of the rule, which is just a bunch of terminal commands that you need to run to make the final target using the requirements. So like, for example, to make the a.o file, what do I require to exist? I need a.cpp to exist first. And then once I have that, what's the body of the rule? How do I build a.o from the required things, from the ingredients a.cpp? I need to run g++-c on a.cpp, and that will create a.o. And so that's one rule. I can do a rule for b.o. It requires b.cpp, and you just need to do g++-c. And then you can make a rule for your final executable, main. What does it need to exist? If we want to do separate compilation, well, we better have a.o and b.o first, and then to create main out of them, we're going to say g++ and link them together, and call the final thing main. So now I've got a makefile that will do what I want. All right. You can say make and then the name of your target. Like, what do you want? I want A.O, make B.O, make main. Like, it'll do it right, and like it'll run those rules and it will all work. But let me get back to a blank slate. If I don't even have anything compiled and I just say I want main, please, it will go and notice A.O and B.O don't exist, and then it'll go looking for rules to make them. And so it'll find those rules, and it's just like, you say what you want, it'll make all the intermediate things, and then build the final thing you cared about, which is beautiful, all right? One last cool thing is you can put the rule that you care most about at the top, the very first rule, and then you can just say make, and then just make by itself will run the very first rule. And so that's usually the one that you put up top there. Yeah, that's pretty much it. And the beauty of makefiles is it will notice, right? This will notice whenever something changes. So let's change a.cpp. Let's say call it on 43 instead of 42. So now if I just say make, and it will make main, it will notice that I did not touch b.cpp. b.cpp did not change, so it does not need to remake b.o. But it will notice that a.cpp changed, and therefore it needs to remake a.o. Watch. It will recompile that only, keep b.o the same, and then link them. Link it with the old b.o. Isn't that cool? That's exactly what we want here. All right. One final thing that people tend to do in makefiles, and I've done this for you, maybe you've seen it, is sometimes people make a rule called clean. It doesn't make a file called clean, but it kind of like cleans up the directory. So a clean rule usually removes all the compiled files. So I'll make a rule called clean. Its job is to just clean up. It has no ingredients. It's like, all right, how do I delete everything? All the compiled files. It's going to be a.o, remove a.o, b.o, and main. And then you give a -f to say, don't complain if those files don't exist right now. Just like delete them if they're there. Don't complain if they don't exist. So now I can say make clean, and that will get me back to a blank slate with no compiled files. And now I can just like do it all from scratch if I need to for some reason. So yeah, that's makefiles and the make command in a nutshell. All right, so what else? Let's talk about inheritance next. So the beauty of inheritance is you get to reuse code across classes. You don't have to reinvent that wheel, okay? So you get that through like you're inheriting just methods in general, and you're also inheriting member variables. And then one cool thing you can do is have virtual methods that let you override the base class's stuff. All right, so my silly pre-made example is going to involve the age-old battle of popular phones. So I'm going to make a phone class. That's going to be the base class for every possible phone. Right? Here's my phones class. I need to be careful and give myself enough room, I guess. So the phone class will represent a generic phone. So let's say that it's got the fields. Every phone has a price, has a battery life in like hours or something. Battery life. And then it's got some methods as well, like getters for those things. And just for fun, I'll make an is an Apple product. Is this thing an Apple product method that returns true or false? It'll be an abstract method though, because this is a generic phone. And then I'll have two subclasses of the phone class. I'll have an iPhone class that inherits from the phone class. This is just a silly example, but it'll practice the things we need to practice. And then it will inherit all of these methods as well as fields. So on top of price and battery life, let's add like a processor model, because Apple really likes to tout their new processor model each year. So I'll add that, as well as some other methods. Like we're going to have a getter for that new field. We'll override is an Apple product because it needs to return true. So that's iPhone class. And then we'll have like an Android phone class to represent an Android phone. I don't know the best model of Android phone, so I just said Android phone by itself. Kind of generic still. Oh well, you can subclass this if you want to, I guess. And so it can have its own new stuff. It can have, I guess I won't add any new member variables, but I'll add a new method, like runs Linux, because Android phones do run Linux, and that will return true, of course. And then it also needs to override saying it's not an Apple product. Okay, so that will be my silly inheritance example, and here it is. Boop. So here's the setup. Here's the phone class. It's got these things, right? It's got some fields, and they are protected fields because I want people to get them in their subclasses. I want the subclasses to have access and control over these fields, so I'm going to mark them as protected. All right, I get to use them in subclasses when I do that. And then I'll make a constructor for phones, takes price and battery life and sets those fields. And then I've got getters for those things, of course. And then I'll make a virtual method called isAnAppleProduct, and it'll be a pure virtual method. I'll say equals 0. It's supposed to return a bool, but I've given no implementation at all right now. So I've marked this as a pure virtual method. It has no implementation up in the phone class. And so it's the job of all the subclasses to actually implement this. This phone class, because it has a pure virtual method, it is going to be marked abstract now. It is called an abstract class when that happens. And that means, because it doesn't have an implementation for something, you can never make a phone object just by itself. So you cannot run this line. Like you can't just say, make a phone object, call the constructor, because you can't run all of its methods. It does not have implementations for all of its methods. So it's an abstract class only, all right? So it's forced to be subclassed, okay? So here are my other classes, iPhone class, subclasses. That will do a processor model. Even though this is the end of the line, I could have said private, but usually when you're doing inheritance hierarchies, you're just going to say protected all day long. And so there's the new field, processor model, and then the iPhone constructor still needs to get and set the battery life and the price, as well as the new thing. But you can use the constructor for your base class, for the phone class, to do that setting. Just like in the initializer list, you can hand off the problem to your base class's constructor, and then you deal with setting the rest of the things, the new stuff, okay? Then there's the getter for processor model, and then here I am overriding the isAnAppleProduct virtual method. So I'm actually giving it a body. It's like, yeah, true, because this is an iPhone, right? And then you like to say override just to convince yourself. It helps the compiler know that, okay, yeah, this was a virtual method, I'm overriding it. I'm making sure that this is my implementation for every iPhone object. All right, so there's that one. And then Android phone is similar. It inherits from phone. The member variables price and battery life. You still need to set them in the constructor, but you can just hand off the problem to the base class to do that setting for you. And then you just need to do all the new stuff. So do the override, like make sure this is not an abstract class. You got to give a body for that virtual method. Pure virtual method is an Apple product. That will return false for Android phone. Then we can add our own new methods just for Android phone objects as well. Like, all right, runs Linux will return true because every Android device is running a version of Linux, which is cool and nice. All right, so that's the inheritance hierarchy. Those are the implementations. I was just lazy and did it all in the class, but you could do that outside the class as well. And then here I am using those things. All right, so let's compile and run this. All right, some cool stuff. I'm just going to future-proof this example and be like, all right, this is going to be iPhone, not iPhone 16, 17, 18. This is iPhone 42 a decade from now, or 2 decades from now. And then I'm just calling the constructor. What am I doing here? Constructor for iPhones sets the price, battery life, and model of the processor. So it's like, all right, it's $10,000. It has a week-long 10-day battery life, 240 hours, and it's the A24 processor. Several processors from now. So yeah, there's that call to the constructor, and then Android phone as well. Here I'm calling the Android phone constructor to create an Android phone with a price and a battery life. It's cheaper, and the battery only lasts for like 2 days or something, which is still awesome, right? Compared to current models. Maybe one day we'll get there. And then you can call all the stuff, right? So I can call like iPhone 42, get its processor model. It's like, oh, it's the A44 processor. it's price. Like all those things work, even though this is from the base class, right? Get price. That was a base class implemented thing. Like that's fine. I inherited that. Is an Apple product is of course true. Then I can do the same thing for the Android phone. Like battery life is an Apple product. 48 false. And runs Linux. Yes, true. Cool. Right? So that's the idea. Yeah, and then the last thing that you can do, the whole point of having virtual methods is that you can override things and you can treat all of your subclasses like a base class and just use the phone features. Like I can make a vector of phone references or phone pointers. It's got to be references or pointers to get this ability. And then I can put in these guys. I can put in the address of the iPhone and the address of the Android phone and treat them like phones. Treat them like the base class. I can only do the phone stuff, but that's fine. Like that's why you put all the stuff you might ever want to call, like this thing, even though it doesn't have an implementation in the base class. You still say that it exists, so that when you do this, like you know that you are able to call is an Apple product. Like the base class or the subclasses must have overridden that thing. So you can do stuff like this, like whatever this thing was at index 0, treat it as a phone star, but like you're actually going to get through the virtual table, if you remember, right? The V table. You're going to get the right thing. That's going to be the iPhone is an Apple product, returns true. You're going to get the actual implementation. Even though for phones, right, for generic phones, we gave no implementation, it's going to get the right one. It's going to notice like, okay, yeah, this is a pointer to an iPhone, is an Apple product, has an implementation for iPhones, and it's this one. I'm going to return true now. So yeah, that's inheritance in a nutshell. It lets you reuse code and then also treat your subclasses as the base class, which is really, really good for implementing common functionality. All right. I think the last big thing that I want to talk about is Huffman coding. So that's going to do compression, right? It builds a really cool tree, a Huffman tree, but it's also an example of a data structure called a trie as well, because along the edges of the tree that you're building, it's actually building strings, right, all the way down. So like this D represents 1, 0, 0. It's a binary trie, okay? It's pronounced a little weird, but that's okay. And then to generate this Huffman tree or this trie out of a file, you're going to do the following. All right, to generate Huffman codes for a given file that you want to encode and compress, you're going to first make a frequency table, calculate the frequency of every character that ever occurred, like count all the A's, the B's, the C's, the D's, all those things. And then you're going to make a priority queue, essentially a heap, right? A heap of nodes, all right? And you're going to make leaf nodes initially for every character and attach their frequency that they appeared in the file in leaf nodes. And they're going to put them all into a min priority queue based on that frequency. So you're going to pop off the least frequent things first, all right? And the name of the game is to repeatedly pop the 2 least frequent subtrees, you're going to eventually build subtrees, and then combine them into a bigger tree node, an internal node, all right, that has a combined frequency, all right? You're just going to sum up the 2 frequencies of the things that you're adding together and fusing, essentially. I'll show you that in a diagram in just a second. Let me get through with the words first. And then the very last time you use, you're going to keep on doing this, and it's going to keep whittling down the size of your priority queue one by one. Eventually, you're going to have 2 big trees left, more or less, usually. 2 big trees left to combine one last time, and that's your final thing. It's one last big tree with a frequencies value equal to the number of characters in the whole file, because it represents them all at once, essentially. Okay, so with that in mind, let's actually have an example. All right, let's say, very silly example. I'd like to compress the string "Hi Mom" without any spaces. So the first step in Huffman coding is let's calculate all the frequency of all the characters in the file or the string you'd like to compress. So like, all right, let's make the frequency table for "Hi Mom." What are all the characters? There's H, there's I, there's M, and then there's O. And how often do each of these occur? The H appears once, the I appears once, the M appears twice, and the O appears once. There's my frequency table. And then what I'm going to do is I'm going to make a priority queue, PQ. And the very first thing I'm going to do is I'm going to put nodes, I'm going to make nodes for each of these character frequency pairs. So my first frequency priority queue looks like this. It's got these nodes in it. The H mapping having frequency 1, the I having frequency 1, the M having frequency not 1 but 2, and then the O having frequency 1. Okay? And so that's my initial priority queue. And then what you do is you pop it. You pop the 2 least frequent things. Pop 2 nodes and combine them into a bigger thing. And because it's a min heap, you're popping the 2 least frequent things. So let's say, I guess we got a tie between these 3, right? The things with frequency 1. So let's say that we're going to pop the H and the I off first, and we'll combine them together. So I'll take the H and the I, H1, I1, and I'll combine them together into like a super node that's a frequency 2, because that's their combined frequency. All right. So I'm turning this priority queue, and then I'll push this back inside the priority queue after popping those 2 off. And so just as a drawing form, the new priority queue looks like this. It's got this in it now, as well as the old stuff. The M and the O are still there. M2O2. And then what happens next? All right, what's the new state of the priority queue? We're going to pop off the 2 least frequent things. So it looks like they're all priority, or sorry, this is priority 1, isn't it? The O is totally going to get popped first, and then it's a tie, right? It's a tie between these 2 guys. What will I pop next? Just to make it easy for the diagram, I'll pop the M as well. I'll pop the M and the O. And then I'll fuse them together, all right? So I'll fuse them together to look like this. It'll be O has 1. O has 1 frequency, M has 2 frequency, and then I'll combine them into a node with size 3 frequency. Okay, so that's the new thing. And that will go, can I drag this? That will go into my new priority queue. All right, I'll take that, and then I'll also take the old thing. That's still in there. So I'm drawing you all the stages of the priority queue as it's changing. Come on. There it goes. So there's my new priority queue. And this is like, our hand is forced now. We know what we're popping next. We've only got 2 subtrees left. So that's my priority queue. The last thing that happens is we pop them both off and combine them. We fuse them together into one big super node of both of them combined. So can I get these off easily? I've somehow lost the ability to do that. There it goes. I gotta copy, or sorry. Let me try and draw a better line. Ooh, nice. One last time. I'm gonna fuse them together to into my priority queue. And then this plus this is combined frequency 5, right? 2 plus 3 is 5. That's the frequency of the whole file at that point. They've all been combined, and there's my priority queue now. I'll push it back, because we're just following the algorithm. There's my priority queue, and the second you have one thing left, one element left, just one big value, one big tree, that is your Huffman tree. You've made it, all right? And so it's a try, because along each edge, like, you're eventually going to get to these characters, right? They're your leaves, and if you go left in your tree, it's a 0, you're adding a 0 to the encoding, and if you go right, you're adding a 1 to the encoding. And so that means that every time you want to encode an H, it's not 8 bits anymore as like a char as an ASCII value. It's going to be 0, 0 to make the H character. Does that make sense? And so, like, to encode hi mom now, it's going to be 0, 0 for the H, 0, 0 for the H, 0, 1 to get to the I, and to decode it, you just follow the tree again. 0, 1 to get to the I, and then M is going to be 1, 0, O is 1, 1, and then M again is 1, 0 again. All right, and so how many bits to encode this? 2, 4, 6, 8, 10, right? This is 10 bits. This takes only 10 bits to encode this string now, instead of, if you were to store this as like an array of characters, each char takes up 8 bits. It's a byte long, instead of 8 times the 5 characters, which was 40, right? It would have been 40 bits. So you've saved it, you made it a quarter the size just by encoding it in this way. You still need to give somebody the tree still, though, to do the decoding, but that's still pretty nice, right? For long files, this really works out well, because you tend to use, like, vowels more often than vowels and spaces, right, than other things. And, like, the lowercase letters appear more often than the capital letters in English writing. So Yeah, that's pretty cool. That's Huffman coding. It's a nice combination of a lot of things. It's like priority queues plus trees all at the same time. Like you're using hash tables to keep track of frequency. That's why we do it last in this class. It's a really good example of everything all at once. All right. So yeah, that's those are the newer things that I wanted to go over with you. We've made it to the end of my slides, so the end of my review lecture. And I guess the last thing I really want to tell you is good luck. Good luck on the exam. I know you can do it. I believe in you. Come to office hours before if you have any questions about anything. I'm happy to help and go over things with you. But I think that's everything that I wanted to review. So thank you for watching this, and good luck.